Hi, good morning, everyone. My name is Christina Vides, and I'm currently wrapping up my PhD at UC Irvine. And today I'm going to tell you about my PhD thesis in 11 minutes, which is a survey that I've been leading called the Search for Protoplanets with Aperture Masking, or the SPAM survey. And I'm going to tell you how we've placed new statistical constraints on the close-in protoplanet population using NERC2. Shortly after star formation, the circumstellar material is flattened by angular momentum, forming a protoplanetary disk. Transition disks are a type of protoplanetary disk that have complex substructures in them. These substructures may be gaps or rings that are caused by an embedded planet, or spiral arms and warping that may be driven by dynamical planet-disk interactions. These substructures are identified in millimeter and scattered light imaging, but another observational signature of a transition disk is then when we plot the stellar accretion rate as a function of disk mass for a sample of stars with protoplanetary disks, we find that stars with full protoplanetary disks have a higher stellar accretion rate than those with transition disks. So we say transition disks are in a stellar accretion rate deficit. This deficit may be caused by the interception of material by an actively forming planet or a protoplanet. So naturally, the best place to search for protoplanets is within transition disks. Here we have a planet mass as a function of some major axis for all of the confirmed exoplanets, including planets that are predicted by these disk features. So disk features have been really only probed down to about 10 AU, but they serve as valuable inputs for planet formation models. And there's really only a handful of unambiguous protoplanet detections. And these detections occupy an outlying region in the mass separation parameter space, which really opens up some questions about migration and scattering. So two of these, the most famous detections, are PDS70b and PDS70c. PDS70c is located near a dynamic disk feature. And these are two examples of planets that were identified with a traditional direct imaging method, such as a coronagraph. And one reason why we may not be detecting planets that are closer in, it may be because coronagraphs are restricted to about 3 lambda over d for their inner working angles, and transition disks are located in star-forming regions, which are located distances very far away, greater than 100 parsecs. So this introduces an observational bias. But having direct imaging data of protoplanets and transition disks is very valuable for understanding the timescales on which planet forms and how planet-disk interactions affect the circumstellar environment. One observational tool that we can use to overcome these observational challenges is non-redundant masking, or NRM. NRM is an aperture masking technique where we place a mask in the pupil plane of a telescope and it converts it into an interferometric array. The mask, which is shown here, has several holes, and a pair of holes forms a baseline. And no two holes have the same orientation or separation, so each baseline has its own unique spatial frequency associated with it. The image we see on the detector is the resulting interference fringes, or the interferogram. And when we take the Fourier transform of the interferogram, we can calculate two Fourier observables, the squared visibilities and the closure phases. And in the calculation of the closure phases, we can characterize and eliminate the speckle noise that limits traditional direct imaging methods and get moderate contrast down to and within the diffraction limit. And contrast is defined as the difference in brightness between the host star and detectable planet signal. What we can also do with these Fourier observables is reconstruct an image, which tells us about the source brightness distribution. So today I'm going to tell you about the SPAM survey, which is a direct imaging survey of transition disks with NERC2 and NRM at L-band. We do the survey at L-band because this is where protoplanets are the brightest in both theoretical SEDs and the observed SEDs of the PDS70 planets. The goals of the survey are to detect and characterize rapidly accreting giant protoplanets in a significant sample of transition disks. So we have imaged 30 transition disks around Herbig AE stars and T-Tauri stars. We'd also like to characterize disk structure and dynamical interactions within the inner regions of transition disks. And we'd also like to constrain the underlying protoplanet population and timescales under which they form. So here I'm showing a few disk detections from the survey. I'm going to first talk about how we've characterized disk structure in the HD34282 and V892 tau disk. And then I'll talk about the point source detection. And lastly, I will end with constraints on the timescales of planet formation. So jumping into HD34282, HD34282 is a well-studied transition disk. And it's been studied in ALMA, millimeter continuum imaging, and in J-band polarimetric images. And in both studies, it's been found that there is an 88 AU cavity as measured from the host star to the inner edge of the disk. And from the ALMA imaging, it's been predicted that there is 50 Jupiter mass companion that is opening up this cavity. We imaged HD34282, NERC2. So here we're showing the reconstructed image from the data Fourier observables. And we also fit geometric models to our data in Fourier space. And we take the best fit Fourier observables, and we use those to reconstruct an image because we want to check that the geometric model can visually reproduce the reconstructed image. And we also explore a couple different scenarios. We fit a single Gaussian ring and a double Gaussian ring to the data, and we find that including a central component, so a double Gaussian ring, best reproduces the data visually and statistically. So we've explored a few different scenarios for what could be causing this complex geometry. So for the physical interpretation of this disk, we find an inner structure where we do not resolve the inner edge of the structure, but we resolve the outer edge at about 20 AU, and this is a spherical brightness distribution, or a spherical distribution of possibly diffuse material. And then we re-resolve the outer disk from about 61 to 78 AU. And we find a 41 AU gap between the two components. So this inner structure could be the result of stellar halos from planetesimal collisions. So what would be happening is there's a rapidly migrating inward planet, and that's causing planetesimals to be flung everywhere and dust to be ground down. There could also be some 3 to 9 Jupiter mass companion could be opening up this 41 AU gap. This is based on equations derived from hydrodynamic simulations, and the 3 to 9 corresponds to typical disk viscosities. And lastly, by comparing our data to hydrodynamic simulations, we found that 2 Jupiter mass companions could also open up a 41 AU gap. So we show that this is a statistically good fit by showing that our Fourier observables are well correlated to the models. And we also calculate our 1 to 5 sigma contrast. And we convert our contrast to absolute magnitudes predicted by hot start models and find that we're sensitive to a 40 Jupiter mass companion at around lambda over d. And that in turn rules out the 50 Jupiter mass companion predicted by the ALMA observations. We also find that we're sensitive to an mass times accretion rate of 10 to the minus 6 Jupiter masses squared per year. And this translates to about a 1 Jupiter mass companion accreting at less than 1 million years. We've also resolved the V892 tau circumbinary disk. So V892 tau in previous literature has been shown to have a circumbinary disk that has a major axis of about 26 AU. At L-band, we re-resolved that circumbinary disk, and we followed it up at K-band to try to disentangle disk features from the binary companion signal. And we newly resolved a circumprimary disk at K-band with a major axis of about 2 AU. We also use R astrometry and archival astrometry to update the orbit of the binary companion. We've also identified disk features a dynamic point source in this survey. So we observed this companion in 2019, and the point source, or possible companion, this point source is located about 10 AU from the host star. We followed it up again in 2021, and we found position angle evolution over time, but this object does become more extended. And this could be a possible companion near an extended feature, which is similar to the PDS-70C observation. And this really motivates the need for having a simultaneous spectral information along with photometric information, because we can both search for position angle evolution and also be able to disentangle disk features from a companion signal. And for the overall survey, we show our contrast limits for a subset of targets in the survey. And we find that we achieve contrast between 4 and 7 magnitude. And this is very representative of the entire 30 targets in the survey. We also convert these limits to mass times accretion rate and constrain mass times accretion rates for the objects in the survey. And this is also very representative of the typical values throughout all 30 targets. And lastly, as I introduced at the beginning of this talk, stars around transition disks are in a stellar accretion rate deficit. And we show how we're sensitive to stars accreting at planets accreting at some fraction of the stellar accretion rate deficit by plotting the detectable accretion rate onto a 10 Jupiter mass companion as a function of stellar accretion rate. And we find that for most of the targets in the survey, we are sensitive to a 10 Jupiter mass companion accreting at 10% or less of the stellar accretion rate deficit. If we were to do this for a 1 Jupiter mass companion, it would be 100% or less. So I will leave my discussion conclusion up, but before I take questions, I'd like to thank everybody at the Keck Observatory. This survey would not be possible without the support astronomers and the observing systems and the staff that made this all possible. Thank you.